Welcome back to my channel. So this will be more of system design. I'm trying to find the book Clubman. Maybe I'll move this over here. I'm mainly doing this because in my job I'm currently struggling with system design and also coding. So maybe I become better at these, and also hopefully I'm just trying out different things, as in trying to see design, system design, or trying to learn computer science in a different perspective, more with human analogy. Last time I was at, hopefully, let me share my screen. So we deliberately induce faults. That's what I was having last time. Clubman. Klepman, where is the book? Klepman. We're deliberately inducing faults. We thought of that. A rare but small discussion on a topic can reduce your fear. Okay, next would be the hardware faults. Whenever I think causes hardware faults quickly come to mind. Hardware disk crash. Give it back. Whenever I think of system failure, hardware faults quickly come to mind. Hard disk crash, RAM becomes faulty, power grid has a blackout, someone unplugs the wrong. Um, on a storage cluster with 10,000 disks, the first response is usually to add redundancy. Um, right configuration. Servers may have dual power supplies, hot swappable CPUs. In data centers may have batteries and diesel generators for backup powers. When one component dies, the redundant component can take its place while the broken component is replaced. This approach cannot completely prevent. Okay, we just add redundancy. Um, However, as okay, redundancy was fine. Using larger number of machines, which proportionally increases the rate of hardware faults. Moreover, it's fairly common for virtual machine instances to become unavailable without warning, as the platforms are designed to prioritize flexibility and elasticity. Hence, there is a move towards systems that can tolerate the loss of entire machine by using software fault tolerance techniques in preference or in addition to hardware redundancy. Such systems also have operational advantages. A single server system requires planned downtime if you need to reboot the machine, machine to apply operating system security patches, for example, whereas a system can tolerate machine failure can be patched one node at a time, a rolling upgrade. I think this is where Kubernetes can help. Basically, you schedule it, you have a Dockerized way container which can run on any type of node pool or machine. I mean, depends on the node pool as well, but all the CPU node pools can take it. So if one of the machine is down as well, the Docker container can be scheduled on another node and the Docker image, and it can run. So we usually think hardware faults as being random and independent from each other. One machine's test failing does not imply it's going to fail. There may be weak correlations, for example, such as temperature in the server rack. Otherwise, it's unlikely that a large number of hardware components. Okay, usually hardware components don't fail at the same time unless they're in the same data center and the data center lost its power. There's no generator over there. Um, Another class of fault is the systematic error within the systems, because software faults may be correlated. They are called systematic errors. A software bug that introduces every instance of an application server to crash when given a particular bad input. For example, consider the leap second on June 30. It caused many applications to hang simultaneously due to a bug in Linux kernel. I think, can I separate software and hardware in terms of human analogies? I don't know, maybe not. I can't think any example which can separate hardware, what's hardware and software. I mean, usually hardware, let's say our body parts are the hardware, and how they function. Can I say our body parts are the hardware? Hmm, not really, but um, maybe it's just, yeah, we are hardware. Let's say each human is hardware on Earth, and the language we speak and the way we function together is more of software. So if, let's say, one human fails, there's another human who steps up for you. So that's just redundancy. Hmm. So instead of considering just one human and seeing from their perspective, what if we see, of course, different, each human is a node or a VM or a database system, and they function towards a common goal. um, I mean, they function towards multiple common goals, but they function. They can we can assume that, let's say, my company, there are 20 employees. Each of them is a hardware, and we are making them. We are making the systems work. So we interact with environments. We perform some actions like typing, like thinking, like communicating. So those are all part of the software. So we use hardware and things like communication for software. But what if, let's say, I introduce a bug, like me as a hardware, write something and introduce a bug in the core platform. Um, then the complete use case might fail because of the simple bug. Um, okay. Similar, I mean, let's say I introduce a bug where um, I write code which cleans out the database every day. Then my it's because of me the entire platform is down, and so entire team is facing downtime because of my bug or because of my skill, the way I wrote the code. A runaway process that uses up some shared resource. Okay. Systematic error within the system. Hard to anticipate. Examples. My own example would be me as a hardware, uh, or our company team, hardware, with nodes, or maybe my brain is my database. I have a group of database, but if my database fails, it might be linked that if I fail, usually the team doesn't fail, but if the software I write fails, or I don't know, I can't. Okay, it's a bad analogy, but I'm trying something. Let's see. When the code I write introduces a bug, core component say database I don't know. Maybe I should think of a better example. Um, let's say, okay, a group of people are going on a hike. Um, to complete the hike is the machine. What happens when someone okay, what happens when someone um, mixes poison in the food which everyone eats during the hike? So that's like a systematic error because of one person failing, or one process failing, the entire ecosystem goes down. And um, okay, a group of people are hardware systems going on a hike. Goal is to complete the hike. Good experience. What if in the route someone takes a shit, spoiling experience for others? And goal is a service that system depends on slows down and starts returning corrupted responses. Cascading failure, where a small fault in one component triggers a fault in another component, which in turn triggers further faults. Okay, basically we need to learn how to avoid these. That's the next question, right? Um, There's no quick solution to the problem of system, and lots of small things can help. Carefully thinking about assumptions and interactions in the system, thorough testing, process isolation, um, allowing processes to crash and restart, measuring, monitoring, and analyzing system behavior in production. If a system is expected to provide some guarantee, for example, in the message queue, the number of incoming messages is equal to, it constantly checks itself and raise an alert if a discrepancy is found. I think how to avoid. There's no definite solution. I think I should write on my own how to avoid systematic faults. Um, there is no definite solution, but small things can help. Think about assumptions and how systems interact. Schematic and mm, humans design and build. Okay, I think that's all for today. Maybe I can't do system design and GenKit at the same time. Need to move system design to the mornings. Okay, that's the plan. So each day you spend half an hour, 1 hour in the night, or at least 10 minutes in the night, and then uh, 30 minutes or at least 10 minutes in the morning. Morning goes for system design. Evening goes for open source contribution of Jenkit. That's all. For Jenkit, I'm just starting learning. Go in 5 minutes. Okay, I'm ending the stream.